My talk is about the Cisco, or our journey within Cisco, on how to apply data science to security. And therefore I'm calling it From Sabotage to Pay TV Fraud, showing how similar data science principles can be used for very different security applications, where each one presents its own challenges, and how we dealt with those challenges in each of these domains. So I'm a distinguished engineer. I've been working at Cisco for 20 years, 16 years, dealing with pay TV systems. And pay TV systems, the Cisco technology initially was essentially what's called conditional access or DRM, where we essentially use cryptography to prevent people from accessing the content unless they paid for it. And at this point in my life, I thought that security was cryptography, meaning that you encrypt content, you hide the keys, and now you're secure. Then we moved to IoT systems. And in IoT, we learned that there's much more than prevention, there's also detection. In order to detect different attacks and exploits, which is critical in a secure environment, you need tools other than cryptography, and here is where data science plays a role. So recently, in the past year, I've went back to pay TV, and what we've been trying to do is take a lot of what we learned in IoT in terms of using data science for detection and applying it to the pay TV industry. So the cybersecurity world came up with the field of threat analytics. Now, threat analytics is essentially using predictive analytics, using predictive analytics as a means of detecting zero-day attacks or predicting all sorts of exploits. Now, why this is critical is that virus checkers and IPS and IDS systems typically work based on signatures. Signatures mean that I'm looking for a very specific rule, which means I'm basically trying to defend against yesterday's attacks. I'm always looking for yesterday's viruses, and I can never find or detect tomorrow's viruses or tomorrow's attacks. Data science, or specifically predictive analytics, works based on models. So if I could create a much more abstract general model, I could then find even tomorrow attacks, as long as it's somewhat related to the previous attacks, or I could define normative behavior and use anomaly detection to locate anomalies and also be able to find what's called a zero-day attack, the new and next generation attack. Now, why this is critical, especially in something like IoT, is because if an attack can take down a nuclear power plant like Stuxnet did, or electric grid, then just learning the attack and building, changing the signatures for future attacks, it's too late. You always have to be able to get even the first attack, which is called the zero-day attack. So what Cisco does, and the type of stuff we look for in network security, which is a very well-known usage of data science, are things like data exfiltration, espionage, having malware come and stealing your data from a particular enterprise. It can locate command and control communication, where you have many botnets communicating with the command and control center, and the command and control center typically manages DDoS attacks, distributed denial of service attacks, and other attacks. It can find all sorts of suspicious websites by looking at the domains, the domain names, and how often they change the domain. Typically in security, how you blacklist, there's all these reputation system which knows how to blacklist websites. So the problematic or the rogue websites are constantly changing their domains, and that's a pattern which can be identified using data science. By looking at DNS traffic, it can detect phishing sites, it can detect all sorts of malware. Again, the idea is that malware is typically evolutionary, and therefore once I figure out and I can abstract a particular malware and create a model of web malware, I can essentially detect all forms of that malware, even if it evolves and even if it changed and even if it's slightly modified. And finally, which is the newest type of data science, it's even looking at encrypted traffic like HTTPS and still identifying all sorts of malicious packets by looking at packet sizes and packets and byte distributions. All these are forms of sabotage because typically in network security, one is using malware and viruses in order to encrypt other people's files, delete files, or steal content. And the whole point of data science is to detect it and then allow some remediating response in order to counter that attack. As an example, this is an example from Cognitive Threat Analytics, which is a company that Cisco purchased, of how it detects command and control communication. And you can see that the one computer is redirected to multiple different computers. The computers are in different countries. Some of the countries may be like Pakistan or other countries which are known to be problematic. The domains are ephemeral, they're constantly changing, and all these factors together enables us to, with high probability, to say, this is a command and control communication between a botnet and the command and control center, and therefore it must be stopped. The pattern is pretty much consistent across most command and control communications, and therefore using network security, we can detect and stop the security. Another interesting case is IoT. And this is work we've done in the past couple of years where in a modern day automobile, there are many computers, hundreds of computers called ECUs that communicate over an artery called the CAN bus. Now, one of the problems with the modern automobile is that an infotainment system, which is connected to a 3G network, also communicates via the CAN bus, which enables me with a computer, a laptop, and a 3G modem to send the command disable brakes into your infotainment system, onto the CAN bus, and onto your brakes, essentially killing the driver and passenger, depending on what speed he's going when he receives the command. So now the consequences of an attack in IoT, and the same thing applies to electric grids and power plants, is essentially death and fatalities and not just deleted and encrypted data. So one of the things we did is we created a model of the CAN bus, of the normative traffic on a CAN bus in order to detect anomalies and stop them right away to prevent a driver from being potentially killed by a cyber attack. We actually attended a major contest by one of the leading US automobile manufacturers and won the contest showing that we had the best accuracy in detecting CAN bus sabotage attacks. One second. Great. So until now I talked about sabotage, which is what I've been working on and which Cisco primarily works on for the past couple of years. And then we started looking at the pay TV industry and said, you know, there's a totally different type of not attack, but problem, which security can help us, especially in terms of data science and specifically predictive analytics. And that's what's called pay TV fraud. And how I want to find pay TV fraud is that your paying customers are violating the terms and conditions of the contract, or they're using the systems in a way that's not allowed. And for pay TV fraud, I can use the similar algorithms, all based on behavioral analytics, in order to catch which customers are violating the system. Why this is important is because typically in pay TV, only the paying subscriber can access the content. And again, using conditional access and other technologies, we already have a good way of preventing non-paying subscribers from accessing content. The problem we have is what prevents that paying from subscriber who accesses the content from sharing the content or sharing means of attaining the content with other people, or using the content in ways he's not allowed to use it. And there, cryptography doesn't help, and therefore we needed to rely on data science. Examples of this are credential sharing. I go to HBO or Netflix or MLB.com or any OTT site, and I share my password with my 15 best friends. Now all of us on one paying account can watch OTT or pay TV content. Again, a very known problematic behavior which costs service providers lots of lost revenue in the sense that 15 people are watching content on one subscription and one paying subscriber. Pub viewing is an interesting case where there typically are different costs between a commercial set-top box or commercial television and a residential television. So as a pub owner, I buy a residential TV or residential set-top box and I move it to my pub, so I'm paying the lower fee and watching and getting and showing TV to everyone who comes to my restaurant or my pub. VPN access is very well known, especially in Israel. Netflix offers 11% of the same content as they do in the US, and therefore anyone with lots of content will access a VPN like Hola, ExpressVPN, or PureVPN to watch 100% all the US content, even though it's against the terms and conditions between Netflix and the content provider. And finally, illegal streaming is I could take the content that comes out of my PC or my set-top box or my device, and I can immediately push it to a website and stream it to everyone to watch it, where now the whole world is watching it on a single subscription. So in all these cases, I have a paying subscriber who is authorized to watch content, and yet he's violating his terms and conditions in a way that I can't prevent him from accessing the content because he's paying. But how can I detect that he's violating the terms and conditions? And this is where behavioral analytics and data science comes in. But this is a very different type of case than sabotage, because sabotage is typically a binary classification. Somebody tries to sabotage my network, my automobile, my electric grid, and therefore it's a binary classification. If I see the packet's malicious, I deny it. If the packet's okay, I allow it. If I see it's a rogue website, I'll take it down, I'll blacklist it. If it's a website which is okay, which is kosher, I'll allow that website. But in pay TV fraud, it's my subscriber, a subscriber I don't want to lose. And therefore, it's very difficult to know what policy to implement. Do I warn him? Do I suspend him? Do I cancel him? Do I blacklist him? All these policies are available to me. And it really depends on intent, context, and quantity. How much is he violating the terms and conditions? And what is his intent in violating the terms and conditions? And therefore, the amount of detection is so much greater because I need not only to capture whether he's violating, I need to capture why, how much, when, where, and therefore the data science becomes so much critical because there's so much more to detect. In the case of sabotage, recall is critical because the false negatives could take down my power plant. In the case of pay TV fraud detection, I care more about precision because unless I'm absolutely sure, I don't want to lose a paying customer. And this made us relearn and rethink our approach to data science when it comes to security. So I want to give an example, and the example is one of the examples I mentioned before, which is credential sharing. I have a password. I purchase a subscription to MLB.com or Netflix, and then I share it with a bunch of people. $500 million of lost revenue is happening because of credential sharing. Credential sharing is growing. The younger the generation, the younger the person, the more likely he is sharing. And what's more important is service providers typically have no clue of what sharing is going on the network. They know what's happening, but they have no clue. Which is why pay TV fraud, as we come to notice, we can get the data, but we can almost never get labels, which is why it's pretty much an unsupervised problem and not a supervised problem, which makes it much more challenging. In the case of sabotage with network security, typically there are very no malware that you can receive from all these threat intelligence companies, and you could perform supervised learning. The other thing which we learned very quickly in the case of sharing is that the intent is very different. Some people share because they have a friend. Why should he pay if I'm paying, if we can watch the same content, the same subscription? Other people do it for business. 15 people to get together, they all put $1 in, and they for $1 can watch at least in the time-sharing mechanism a full pay TV subscription. Other people steal accounts. They buy accounts on the darknet that were stolen from Target or from others, and they try it on Hulu and HBO, on Netflix, and eventually it'll work because people typically don't change the password. And in each case, the intent and why the sharing is happening is different. And in each case, the service provider may decide to have different policies based on the different intent. I may want to stop stolen accounts because there my subscriber is actually being hurt than the case of casual business sharing where he's actually part of the problem, which is the case of collusion. So therefore, in the case of sharing, and this is just an example, determining policy requires a lot of information and a lot of detection. For instance, you need to answer, and again, it's an unsupervised problem, is the activity anomalous? In other words, does this account have much too much activity for me to think it's one person using the account? Is the anomalous activity legitimate? Potentially, it could be anomalous. However, it just happens to be that there's a family with large children, there's a businessman who's traveling all over the place and viewing from a different location every day. And therefore, even though it's anomalous activity, it may be legitimate, and this is not a case of sharing. Is the anomalous activity part of within the context of a single family? Maybe if I share my password with my son who's in the dormitory in college, the service provider will be more tolerant than if I share my password with 5 different friends who live all over the world and aren't related to me. And finally, what is the intent behind the sharing? Is it casual sharing? Is it business sharing? Is it stolen accounts? And this is an example of the data science we did to answer all these different questions. Again, showing the wide range of different algorithms and different approaches you need in order to solve a problem within the area of pay TV fraud. But the first thing we did is we collected behavioral data, which is essentially who, when, where, what, and how. Who's watching data? What's the IP address? What's the device? When is data being watched? What's the session time or program time? From where is the person watching data? Where, which city, which location? What data is he watching? People typically watch the same form of data. What's the genre? What's the programs? And even how does he watch data? Does he tune through advertisements? Does he use subtitles? And again, people are creatures of habits, and if I can learn a behavior, I can learn a persona. If there's multiple behaviors, chances are there's multiple personas in this account. The next thing I do is I use these features, and I assume a multivariate normal Gaussian distribution, and I can create, again, it's unsupervised, so I really no labels to build the classification algorithms, and I can determine where are the outliers, how many standard deviations are they away from the mean. And this gives me the potential of all accounts which are sharing. However, like I said, just because you're anomalous doesn't mean you're illegitimate. So the next thing we did is we used what's called a bipartite graph. And this is a very interesting slide. You have 3 different pictures. The first picture is the blue dots are IPs and the red dots are devices. So on the left, you see that there's multiple different devices watching over different IPs all the time. The bottom shows the time frame of the viewing. All 3 are watching the whole month, during the course of the whole month, each at a different location. Clearly, this is a case of sharing because you have 3 different households watching content on different devices, on different IP addresses, and different locations consistently through the month. The right, which is also anomalous, is essentially my life. One device traveling to a different place every day, watching for a short period of time. So the number of locations, which is like 10 over here, is anomalous. But this is not a sharer. This is just a person with a poor family life. Finally, we go to, is it part of the family? So now we take all the different clusters based on the bipartite graphs that we created, and we try to label the cluster. In other words, I can access all sorts of databases like IMDb, which tells me per movie, what's the likelihood of being male and female? What's the likelihood of a person watching above 50, between 25 and 50, from 0 to 25? And I could say, okay, out of the 7 users, I can classify each one, male, adult, female child, male child, female child. And based on that, I can compare it against if the service provider has my family data. Maybe I'll go to a social network and get my family data and see if this is really a family or if this is multiple sharers of different types. So now I answered the question of the activity is anomalous. I answered the question of it's illegitimate, and it's definitely not a family because there's 6 adults and 1 child. And finally, the answer question is, why is the sharing happening? And again, we notice patterns. When you have a business sharing, there's a huge uptake. You're constantly trying to sell. You're trying to make money. So you want to sell your credentials, and there should be a steep graph. When it's casual, you typically will have 1 user. 3 months later, he happens to have a 4th of July or Yom Ha'atzmaut barbecue, and he gives it to a single friend. And it's a very slow uptake. While typically stolen accounts are back and forth, they go up and down, and based on different patterns such as this, the features of the change in number of users over time, I can also detect intent. So now, by knowing the intent and the legitimacy and whether it's a family or not, I give a tremendous amount of information for the service provider to finally make the decision what policy to enact, to suspend, to cancel, to warn, to send a friendly notice. He could do whatever he wants, but without all this information, he really can't do much. In some ways, it's like being a parent. You have so many policies, but you need to know an awful lot in order to implement the correct policy against your misbehaving child. So the takeaway is this, is that Cisco started, along with many cybersecurity companies, using data science to detect and remediate sabotage of networks and IoT based on rich network data. This was typically a binary classification, trying to detect malware, rogue websites, and different sabotage attacks, and preventing disaster in the case of IoT from happening. Cisco then extended data science security for the many complex case of detecting and combating pay TV fraud, where the policy is much more complex, even though the consequences are much more mundane. And Cisco is continuing its journey in data science, trying to apply more and more places within the large world of computer security, cybersecurity, in order to apply data science, in order to protect the future and detect any exploit or attack. Thank you.